All right. You're welcome, Leah. All right. Welcome back, everyone. Let us finish this out. Hospital noise levels. For a sample of 6 operating rooms taken in a hospital study, the mean noise level was 38 decibels and the standard deviation was 11.8. Find a 90% confidence interval of the true mean of noise levels in operating rooms. Now, they mentioned nothing about a population standard deviation, so this is going to be a T interval. So T interval, and 38 is the mean. Standard deviation is 11.8. N is 6. Confidence level is 0.9. So I'm getting this as my answer. So this is 28.29 decibels up to 47.71 decibels. How are we doing? All right. Next up, number 30. A federal report indicated that 26% of children under the age of 6 live in poverty in Tennessee, an increase over previous years. How large of a sample is needed to estimate the true proportion of children under age 6 living in poverty in Tennessee within 4%, with a 99% confidence? Okay, so we have a lot going on with this one. The formula that we're going to be using is here. And we know that P hat is 0.26, which means that Q hat is 0.74. It's the complement of P hat. And they say E in this case is the 4%. They also give us alpha, which is the 1%. Alpha over 2 is 0.5%. And Z sub 0.005 is going to be inverse norm of 1 minus 0.005. And it doesn't say, but I'm going to round it to 3 decimal places. To use with the formula. So my N is going to be 2.576 squared times 0.26 times 0.74 over 0.04 squared. So if this is a test question, I'm going to have to go in by hand again, because this is slightly different than the answer key. Yeah. Off by 3, and it would still mark you fully off. So I'll have to keep an eye out for that when I'm grading. So that is my answer. Now, if you use more or less decimal places, then that's going to change that number just slightly. All right. I would like to move on. A study of life expectancy showed that a random sample of 6 states had a standard deviation of 0.8 deaths per year. Find the 80% confidence intervals of the variance and standard deviation. Assume that the variable is normally distributed. Okay. So let's start here. All right, and in the middle here, and this is going to give us our chi-squared left and our chi-squared right. Our n is 6 in this case, which means our degrees of freedom is 5. So degrees of freedom is 5 with 90% to the right of the chi-squared L. So 90 and 10%. All right, so we are at 5 degrees of freedom. And we are here and here. So here and here. 1.610. So 1.610. The other one was 9.236. We okay with the chi-square table? It's not too bad. And Shanny, you've been consistent all semester. Thank you once again for having your camera on. It's always great to see your smiling face. All right, so let's do the variance one. This is going to be standard deviation is 0.8. And I'm going to also do the square root with it so I can get the standard deviation version. So this is going to be 5 times 0.8 squared divided by 9.236. This is round to 1 decimal point, so that's 0.3. The square root of that is 0.6. We'll do the other side of that now. So 5 times 0.8 squared divided by 1.61. Really? Exactly 2? Oh, yeah. Huh. Weird. 2 and then the square root of 2. Yeah. 2.0. And then the square root of 2 is about 1.4. Any questions with that one? I know these are always a little much when you have to actually do the formulas themselves. All right, let's keep going. And we are to hypothesis testing. Thanks to an initiative to recruit top students, an administrator at a college claims that this year's entering class must have a greater mean IQ score than that of the entering class from previous years. The administrator tests a random sample of 11 of this year's entering students and finds that their mean IQ score is 116. With a standard deviation of 12, the college records indicate that the mean IQ score for entering students from previous years is 113. So let's start there. So this is mu is 113. And he's claiming that it's bigger than 113. This is going to be a right tail test. They say nothing about the population standard deviation. Yeah, I don't see anything. So this is going to be a t-test. And to get the critical value, I have to use inverse t. And the degrees of freedom, so n in this case is 11. So the degrees of freedom is going to be 10. Oh, by the way, yesterday, remember I said that calculator wasn't working right? I finally figured out what I was doing wrong, and I knew it was something I was doing wrong. And then the 10. So 1.812. All right, let's use our t-test. Mu in this case is 113. X bar 116. Standard deviation is 12. N is 11. And this is a larger than. All right. So this is a t-test. And the test statistic we have right here. So this is going to be t is about 0.829. The p-value actually, I don't need that. 213, yeah. All right, so let's come to a conclusion here. First of all, I can see that my test statistic is nowhere close to the critical value. And I can also easily see that this is way bigger than my alpha, which means we are going to fail to reject the null hypothesis. Would we conclude that it's greater? Nope, we would not. Any questions? All right, let's keep going. A company announced that the mean breaking strength of the cables it produces is 2,140 pounds, with a variance of 36,056. A consumer protection agency, skeptical of the consistency among the company's several factories, claims the actual variance is higher. So let's get that here. So this is going to be the variance is equal to 2140. This is going to be larger than 2140. The agency takes a random sample of 26 cables produced by the company. The cables have a sample mean breaking strength of 2,148 with the sample variance of 59,953. Is there enough evidence to conclude at the 5% level of significance that the true variance is higher than that? All right, let's draw a picture. And because it's larger than this, it's going to be a right tail only. And this is 5%. So the area to the right is 5%. Degrees of freedom is 25. So we are at 5%, so we're up here. And degrees of freedom is 25. That is way down here. So that's going to be here, I believe. Let me see. Yes. So 37.652. 37.652. 37.652. This is clearly going to be a chi-squared. Oops. Chi-squared test. Degrees of freedom does apply here. Degrees of freedom is going to be 25. All right, so we need to find the test statistic and the p-value. The test statistic this is 25 times 59953 divided by, oh, this is wrong. That should be 36056. 36056. So 25 times 59953 divided by 36056. So I'm getting that the test statistic is 41.569. And I can easily see that that is in the critical region there. The p-value, so this is going to be way over here. And the p-value is going to be this area here. So the p-value is going to be chi-squared CDF of 41 point, this is hard to write, 41.569, comma, big number. And then the degrees of freedom, which is 25. So this is 41.569, comma 25. And if we round that off, that's going to be about 0.020. I guess it's going to be easiest way to round that off. Which is definitely less than my alpha. Which means we need to reject the null hypothesis. So do we think that it's higher than that? Yes, we do. Yes, we do. Because we're throwing out the null hypothesis, which means we're going with that it's larger. A lot of moving parts on that one. I know the ones with the chi-squared are quite a bit more work.
How do you know the difference between the chi-square, the t-test, the z? Like,
Chi-squared is always about the variance or standard deviation. The t or z is always going to be with the mean. And then when it's a proportion, then that's always going to be a z. That's in your notes in chapter 8. There's a table there that kind of outlines all of that towards the beginning of chapter 8.
what's that test F?
Say it again.
I said, what's that option, the test F?
F, that's going to be like ANOVA. We're not going to deal with an F distribution at all. Yeah.
Got it.
Yeah, we're just going to use p-value for those problems. All right. The owner of a chain of mini markets wants to compare the sales performance of two of her stores, store 1 and store 2. Though the two stores have been comparable in the past, the owner has made several improvements to store 1 and wishes to see if the improvements have made store 1 more popular than store 2. Sales can vary considerably depending on the day of the week and season of the year, so she decides to eliminate such effects by making sure to record each store's sales on the same 12 days, chosen at random. She records the sales for each store on these days as shown below. And once again, I want to make it really clear that we are interested only in their differences. Based on these data, can the owner conclude at the 5% significance that the mean daily stores in store 1 exceeds that of store 2? All right, so let's start here. This is going to be mu sub d equals 0, meaning there's no difference, or mu sub d is bigger than 0. And how I'm getting bigger than 0 is because if store 1 is bringing in more than store 2, then when I subtract them, then that difference should be positive if it's more. All right, this is definitely a t-test statistic. And there are 12 days, so n is 12, which means my degrees of freedom is 11. And let's draw a t-distribution. And this is a right tail. Here we are at 5%, right? They said 5%, yeah. So to get my critical value, I need to do inverse t. This is at 1.796. And I'm just going to run a regular old t-test on this one. Mu in this case is 0. Oh, I got to put this into a list. Didn't put the data in. All right, so 264, 428, 56, negative 218, 1, 295, negative 78, 98, 39. I'll give you a minute to let you get caught up. And now we're going to run a t-test. This is based on data. And our test statistic is T 1.145. We'll do 4.5. Why not? And our critical value, oh, they're doing critical values, but I'll write down the p-value anyway. Even though it doesn't ask for it. You guys will let me know if you're getting something different. And I will say that this is our critical value, 1.796. Now this is definitely bigger than our alpha. Also, I can see that my test statistic is not in the critical region. And our conclusion is you're going to fail to reject. So the answer is, can we say that it exceeds it? Nope, we're not seeing any evidence of that. Still looks about the same. Any questions? Let me let you just get caught up. All right. Several months ago, while shopping, I was interviewed to see whether or not I'd be interested in signing up for a subscription to a yoga app. I fall into a category of people who have membership at a local gym and guess that, like me, many people in that category would not be interested in the app. My friend Salma falls into the category of people who do not have membership at a local gym, and I was thinking that she might like a subscription to the app. After being interviewed, I looked at the interview's results. Of the 87 people in my market category who had been interviewed, 17 said that they would buy a subscription. And of the 99 people, Salma's market category, 21 said that they would buy a subscription. So let's write some of this down. So X sub 1 is 17. N sub 1 is 87. X sub 2 is 21. And N sub 2 is 99. All right. Assuming that these data came from independent random samples, can we conclude at the 5% level that the proportion 1 of all mall shoppers in my category who would buy a subscription is less than the proportion 2 of the ones fall into Selma? So this is going to be P sub 1 equals P sub 2. And P sub 1 is less than P sub 2. Another way this can be written is P sub 1 minus P sub 2 equals 0, and P sub 1 minus P sub 2 is less than 0. I'm looking at the key, and they wrote it the second way. I've never written it that way. I've always written it the first way, but I'm pretty sure ALEKS takes both. Proportions are always at Z. This is a less than, so it's going to be a left-tailed. And this is at the 5% level. And we are going to be running a 2 proportion z-test. Degrees of freedom do apply here. Remember, it's the smaller of the two ends, and 1 minus that. So our degrees of freedom are going to be, so the 87 is less, so this is going to be 86. And that is now, I'm going to get, so I'm going to use inverse norm. Oh, degrees of freedom don't apply here, sorry. Inverse norm. This is negative 1.645. All right. Find the value of the test statistic. Okay, so again, I'm going to run the 2 prop z-test. 2 prop z-test, that's number 6 on my calculator. X sub 1 is 17. Yep. N1 is 87. X sub 2 is 21. And then N sub 2 is 99. And this is a less than scenario. All right, so it looks like we're getting the test statistic Z is negative 0.282. Critical value we have here. Negative 1.645 up, and I'm going to write down the p-value. Even though it doesn't ask for it. Which is over the top bigger than my alpha. I can also see clearly that my test statistic is definitely not in the critical region. So we're going to fail to reject. Which means we're still going to continue to assume that they're the same. So do we think that it's less than? No, we don't. We can't make that conclusion. All right. Let's keep going. And please stop me if you have questions. And if I don't hear anything, I'm just going to keep going. NHL assists and total points. A random sample of scoring leaders from the NHL showed the following numbers of assists and total points. Based on these data, can it be concluded that there's a significant relationship between the two? So this one is going to be rho is equal to 0, or rho is not equal to 0. So we're going to run a linear regression t-test for this one. And I'm going to put this into list 1 and this into list 2. All right. I'm going to go ahead and graph this. If you remember, what you need to do is you need to go to, first of all, clear any functions that are in the y equals category. Then I'm going to hit second and y equals again to go to the stat plot. Make sure you turn one on, which mine is turned on. Then we graph, and I'm going to zoom stat. And try to compare which graphs this looks more like. This is looking like C to me. Yeah, it's just the perspective is just a little bit different, but it's definitely C. So we're going to find the correlation coefficient and the p-value by running, once again, this is a linear regression t-test. Usually way towards the bottom, yeah. So R in this case six, 4, 8. 6, 4, 8. We can stop there. P-value 0.164. Oh, it says 4 decimal places, so that's 3, 8. All right, and the p-value, I already forget what the alpha was. What was the alpha from the original problem? It's being covered up. There it is, 0.05. So this is way bigger than 0.05, which means we're going to fail to reject the null hypothesis. Which means there is not. a significant linear relationship between the assists and local and total points. Boy, that one's all dramatic with the part one, part two, part two. All right, we just have a few more to go. Ages of Head Start program students. The Head Start program provides a wide range of services to low-income children up to the age of 5 and their families. Its goal is to provide services to improve social and learning skills and to improve health and nutrition status so that the participants can begin school on an equal footing with more advantaged peers. The distribution of ages for participating children are as follows: 4% 5-year-olds, 52% 4-year-olds, 32%, 34% 3-year-olds, and 10% are under 3 years. When the program was assessed in a particular region, it was found that of the 200 participants, 1395. So this is we're doing, this is a goodness of fit test here. So let's get some of this information down. So in list one, I'm going to put 13, 95, 82, and 10. Now there were a total of 200 that says. So list two is going to be the expected. So this is the observed. This is the expected. Now the expected is going to be this first one here. It is going to be 4% of 200. It's going to be 52% of 200. It's going to be 34% of the 200. And 10% of the 200. All right, so we have 13, 95, 82, and 10. 0.04 times 200. 0.52 times 200. 0.34 times 200. And 0.1 times 200, that'll be 20. Okay, so here is our two lists. We'll come back to that. The distribution of ages for children participating in the Head Start program are as follows, since they give the percentages. And this is not the claim. Not claim. Distribution is not the same as the null hypothesis. This is the claim. Everybody with me so far? All right. So we're going to find the test statistic. So let's run the goodness of fit. Before we do that, let's draw our fancy little picture and all that. So this is going to be so the test we're going to be using is the chi-squared goodness of fit test. Remember, these are always right-tailed tests. And this is 1%. My degrees of freedom is 1, 2, 3, 4 categories. So degrees of freedom. Remember, K is the number of categories. K in this case is 4, so degrees of freedom is 3. 3 with 1% to the right. Let's see where that gets us. So we have 3 degrees of freedom, and to the right is point. I forgot what it was. 0.01. So that brings us to here, 11.345. All right, so let's run our goodness of fit test. Degrees of freedom is 3. And I'm getting that the test statistic is 11.786. And the p-value 0.0815. And that is definitely less than my alpha. What is the, oh, that's the, so when it makes a PDF like this, it gives the drop-down menus, I assume. That's kind of nice, actually. All right, so we are going to reject the null hypothesis. Reject. Which means there is enough evidence to reject the null hypothesis that the distribution of the ages participating in the Head Start program is given. There it is. Goodness of fit. So I often get students, hey, how do you know it's goodness of fit? Whenever it starts breaking down the categories into percentages like this, that's a really good indication that it's goodness of fit. Now, it doesn't always do that, because if they're all the same, then it's that. But you can also look at the null hypothesis. Yeah. Remember we did the one about the babies being born on different days of the week. And so all of those were the same. They weren't broken down by percents like this one is.
Professor Ryan, does the observed, like the fact that it's split up into the observed and expected values, does that also kind of have an indication of that we're going to be using a goodness of fit test, or could that be like other?
No, for sure that is. The thing is, there's 2 tests where we use observed and expected. One of them is the goodness of fit test. The other one we just do, it's called the chi-squared test. That's when we're with the contingency tables testing for independence. That's where we use the matrices. So both of those have observed and expected. But this one, we know it's this one is goodness of fit because it's just a list versus the next one I'm guessing is going to be a table. Yeah, a contingency table. Did I answer your question, Channing?
Yeah, thank you.
Awesome. All right. So now we are going to be using for this one just a plain old chi-squared test. Oh, I also wanted to point out over here that you can see that my test statistic is in the rejection region. It's a little bit bigger than the 11.3. All right, automobile ownership. A study was done on the type of automobiles owned by women and men. The data are shown. At 5%, is there a relationship between the type of automobile owned and the gender of the individual? So here's our contingency table. And let's start by putting this into our matrix. So this is a 2-row, 4-column matrix. Okay, so now we have that, so we can scroll a little bit. Here, let's quit out of that. The type of automobile is independent. Independent here. Independent of the gender of the owner, and this is not the claim. The type of automobile is dependent on the gender of the owner, and this is the claim. All right, so we're going to find the p-value. So let's go ahead and run our chi-squared test. Once again, this is the chi-squared. And let's set up a little graph here. And I don't remember the alpha. Oh, but we might be able to cheat. It doesn't say, so I gotta scroll back up, 5%. And if you remember that for the degrees of freedom, this is the number of rows minus 1 times the number of columns minus 1. So our degrees of freedom is 3. 3 with 0.05. Did we just do that one? 3 at 0.01. Okay, so we are here. So we end up with 7.815. 7.815. 7.815. Okay, so let's run our chi-squared test. And there's our observed, yeah. So our test statistic, actually, they don't even ask for the test statistic. They just want the p-value. All right. And that definitely seems bigger than our alpha, which is 5%. Which means we're gonna, we're gonna fail to reject the null hypothesis. So, oh, I guess I should use their language. Do not reject the null hypothesis. And summarize the results. So there is not enough evidence to support the claim. There is not enough evidence to support the claim that the type of automobile is dependent on the gender. There is not enough evidence to support that. That's right. Because we're failing to reject. Yes, got it. All right, last problem of the night. Day, whatever it is. I'm guessing ANOVA. It sure is. So this is very much like the one that we did in class yesterday. Cell phone bills, or 2 days ago, I guess. The average local cell phone monthly bill is $50.07. A random sample of monthly bills from 3 different providers is listed below. At the 1% level, is there a difference in mean bill amounts among the providers? Okay, so I'm going to take a few minutes, and this is going to become list 1, list 2, and list 3. And I'll give you guys another minute to finish typing those in. All right, state the hypothesis. We're going to go on the assumption that all of the means are the same. This is not the claim. At least one mean is different from the others. This is the claim. All right. Find the p-value. So we are going to run ANOVA. This is usually the very bottom test. And we're going to run list 1, list 2, and list 3. And there's our p-value. P-value is 0.07986. And I forgot what our alpha was already. Now we'll go back and look. Alpha is 1%. This is definitely bigger than 1%. Which means we are going to fail to reject it. Do not reject. Which means there is not enough evidence to support the claim that there's a difference between them.